Why doesn't a wagon fall through a sidewalk? The answer to that question is that the sidewalk pushes up on the wagon to prevent the two objects from occupying the same space at the same time. The sidewalk exerts what's known as a support force on the wagon. Support forces appear whenever two surfaces try to occupy the same space. My hands, for example, as I push them together, trying to make them overlap, the atoms, molecules, and materials that are my hand begin to push apart. Well, support forces act perpendicular to surfaces. Perpendicular is the sort of universal right angles. This stick is perpendicular to the surface of this book, meaning that it's at right angles in every respect. And the stick actually is experiencing a support force when I push it against the book. Again, I'm trying to make the two of them occupy the same space. They don't like that. The book pushes away with a support force on the stick, and the stick is showing you the direction of the book's support force. There is another kind of force that acts along surfaces. That type of force is known as a frictional force. And we're going to leave frictional forces for the episode on wheels. For now, we're going to ignore friction and look only at support forces. And so if we go back to the wagon, the sidewalk is pushing perpendicular to its surface on the wagon. And since the surface of the sidewalk is horizontal, its support force on the wagon is straight up. That upward force cancels the wagon's downward weight, leaving the wagon here inertial and motionless. That brings us to a question. If I push on a ball, in which direction is the ball's support force on my finger? Wherever I touch the ball pushes on my finger with a support force that's perpendicular to that local patch of ball surface. And that perpendicular direction, which I'm illustrating now with this stick instead of my finger, that perpendicular direction points from the center of the ball to the place where the stick is touching. And I'm just continuing that line with the rest of the stick. So you can see the direction of the support force that the ball exerts on the stick when the two try to overlap in space. The wagon and sidewalk clearly push on one another with support forces. But which one is pushing hardest on the other? The answer to that question is surprisingly simple. They push equally hard on each other in exactly opposite directions. That's an example of what is known as Newton's third law of motion. And Newton's third law of motion is an observation about our universe that says that whenever one object pushes on a second object, the second object pushes back on the first object with a force that's equal in amount but opposite in direction. Every time. So if I push on one finger on the other finger, the second finger pushes back on the first finger equally hard in the opposite direction, no matter what I'm doing. In the case of the wagon on the sidewalk is pushing up on the wagon to support the wagon and keep it from falling through the sidewalk, but at the same time, the wagon is pushing down on the sidewalk just as hard in exactly the opposite direction. Well, Newton's third law of motion, which is often just simplified as for every action there is an equal but opposite reaction, is easy to say, but not so simple to comprehend. To show you all the ramifications of Newton's third law of motion, I need some help and some more room. So let's go outside and show you how Newton's third law works. To show you just how general Newton's third law is, I've enlisted the help of Eris and Ryan, and they're going to push against each other using these spring scales. So Eris's spring scale will show you how hard she's pushing against Ryan, and Ryan's spring scale will show you how hard he's pushing against Eris. And your goal, guys, is to push differently against one another. See whether you can make it so that one spring scale reads differently than the other. If you do, you violated Newton's third law, and we have a Nobel Prize to go earn. Okay? Alas, we're not going to earn it. Watch. Okay? Give it a try. Now, you can do better than that. Come on. It's always reading the same. Just the little secret is the universe is rigged against them. They can't do it, no matter how hard they try. Okay, so that's horizontal. Total failure. You can't do it, right? Now let's try vertically, up and down, okay? 70 and 70, 50 and 50. You can't beat the system. So, once again, the universe demands that whatever force Eris exerts on Ryan, Ryan exerts the same amount of force on Eris in the opposite direction. Okay, thanks. Newton's third law works not just when people are standing still, it works when they're moving as well. And this isn't all that intuitive. It sure seems like if you push on something that's moving toward you, that, well, you don't push the same as it pushes on you. Or if it's moving away from you, again, you don't quite push on it as it pushes on you. The secret is, though, you do push just as hard on it as it pushes on you. You can't beat Newton's third law. And I'll show you that with Eris in a wagon and Ryan pushing on her, both to push her to go faster and to go slower. It won't work. They push equally hard. So here comes Eris, and you can now get ready to push on Ryan. Okay? So no matter that Eris is moving and Ryan is pushing her forward, they're still pushing equally. Now we'll go backward. Here we go. Same thing. Isn't it nice to have a wagon? And how about if Ryan, instead of pushing her that direction, come in front and push her back. You got to turn your scale around. There we go. Ready? Okay. So now Ryan is fighting me, making it harder for me. I'm working harder now, right? And they still push equally hard. And now Ryan can actually make Eris accelerate. I'll stop pushing and they still push equally. We can have all kinds of accidents here. But no matter what, the two forces in a Newton's third law pair are always exactly equal in amount and exactly opposite in direction. I hope you're convinced. Suppose you reach out and push on a passing bus with a force of 5 newtons away from you. What force does the bus exert on you in return? Regardless of what the bus is doing, it will always exert an equal but opposite force on you. So if you push it away from you with a 5 Newton force, it'll exert a 5 Newton force on you in the direction opposite your force, namely toward you. Evidently, the wagon and sidewalk push equally hard on one another. The sidewalk exerts an upward support force on the wagon, and the wagon pushes back exactly as hard on the sidewalk with a downward support force. Well, the wagon is motionless here, which means that it's inertial. It's not accelerating at all. So the net force on it must be 0. We know it has a weight, and yet it's not falling. So the support force from the sidewalk on the wagon must exactly cancel the wagon's weight. And so it does. The sidewalk is perfectly supporting the wagon's weight. Well, before we go on to look at why the sidewalk chooses exactly that amount of force to exert on the wagon, let's take a look at Newton's third law, one last look at it, and recognize that so far I've only talked about 3 forces. The wagon's downward force on the sidewalk, the sidewalk's upward force on the wagon, and the wagon's downward weight. That's 3 forces. That's an odd number. And Newton's third law says that for every one force, there's an equal but opposite force around. We'll deal with the around in the next section. Well, we're missing a force. The missing force is the gravitational attraction of the wagon on the Earth. Recall that the wagon's weight is the Earth's gravitational attraction on the wagon. Lo and behold, the wagon exerts an equal but opposite force, a gravitational force, on the Earth. And that's the fourth force that was missing. And we do have two pairs of Newton's third law forces. The one pair is the wagon's force on the sidewalk and the sidewalk's force on the wagon. The other pair is the Earth's gravitational force on the wagon and the wagon's gravitational force on the Earth. Well, that's enough then about just having the wagon and sidewalk push on one another. Now, in the next segment, we'll look at why the sidewalk chooses to push on the wagon with just enough force to support the wagon's weight.